video, we're going to take a look at the acid-catalyzed transesterification reaction. So we have an example here, just a generic example, showing that we're starting with an ester, and we are reacting it with an alcohol. And what we're doing is we're replacing one OR group on the ester with a different OR group to the ester. So we're taking an ester and an alcohol, and we're making an ester and an alcohol overall. And so you might wonder, what's going to make this reaction occur? We've seen previously, if you have an acid chloride, say, to start with, that you've got a better leaving group than what you're trying to replace it with. But if you're trying to replace an alcohol with an alcohol, your leaving group abilities are the same. So the way that we can force this reaction to favor the products is to use an excess of the alcohol. So use excess reagent here. So often we use that alcohol as the solvent. Okay, so it's often used as the solvent. And because esters are not that reactive, we also need a strong acid catalyst. So what we'll often do is we'll often take our ester and put it in a solution of the alcohol and add in a strong acid catalyst such as sulfuric acid. And this is an equilibrium. So that excess reagent, the purpose of that is to drive that equilibrium towards products. Okay. So we are taking one OR group, and so I'm just going to kind of highlight these in colors. And so that's going to end up being part of your alcohol in the product. And then your alcohol solvent, right, is what's replacing that OR group on the ester. So let's look at an example and run through the mechanism for this. Okay, so let's say we are starting with methyl benzoate. And maybe we want to do a reaction to form ethyl benzoate. So if we're trying to decide on our reagents, we're going to look at what it is we're trying to replace, and we see that we want to replace this with this OCH2CH3. So that tells us that the alcohol that we would want to use as the solvent and as our excess reagent would be ethanol. And then we'd probably use a catalytic amount of sulfuric acid. So catalytic. H2SO4. So before we get started with our mechanism, one thing we want to recognize is when you take a strong acid and you put it in solution, it is going to dissociate completely, right? That was the definition of a strong acid that you would have learned back in general chemistry. So you want to know that when you have a solution that is an alcohol and your strong acid catalyst, that what you actually have, so what is actually present in that solution is your protonated alcohol. So that's that sulfuric acid dissociating, right? So you'd have a small amount of that, and most of the solution would just be your neutral alcohol. So the reason why we're looking at this before we start is we want to know what the identity of the acid and the base/nucleophile is as we go through the mechanism. So this tells us that if we need an acid, if we need to protonate something, that the acidic species we have in solution is the protonated alcohol. So we'd use that whenever we need an acid. And then most of your solution is going to be that ethanol, and this can function as a base if you need to remove a proton, or it can function as a nucleophile, such as when it attacks the carbonyl. All right, so let's start this mechanism. So the first thing that's going to happen is you need to protonate the carbonyl carbon. So we need an acid. So we know that we have that protonated alcohol available to us as an acid. So the very first thing that takes place in this mechanism is you are going to protonate your carbonyl carbon. And this entire entire mechanism is equilibrium, so I'm going to keep using these equilibrium arrows between all of the steps. So we are protonating that carbonyl carbon. And so this is part of how the acid catalyzes this reaction. By protonating this, it's making your carbonyl carbon more electrophilic so that it can react with a weak nucleophile such as an alcohol. And so now we are going to have the alcohol attack that carbonyl carbon. And this attack will look the same as it does for every single nucleophilic acyl substitution reaction. So your nucleophile attacks the carbon and pushes electrons up onto the oxygen, giving you a tetrahedral intermediate. Okay, so here is the structure of our tetrahedral intermediate. So you can see you have the new alcohol that is added. You have an OH group, that's from where you push those electrons up onto the carbonyl, and you have OCH3 as a leaving group. So in order to do this reaction, we need to move some protons around, right? We're not gonna have this collapse and push off OCH3 minus. That is much too strong of a base to exist in an acidic solution. So we need to protonate this in order to make it into a good leaving group. But before we do that, we need to deprotonate here. Our solution is only slightly acidic, so we can justify having a +1 charge, 1 extra proton on this molecule, but we're not going to have a species where we have both of those protonated if we only just have a small amount of acid in our solution. So the first thing we want to do is we want to remove that proton. And so we need a base. So we want to look to what we have present in our solution, and we see if we need a base, we're going to use ethanol. So I'm going to use ethanol to remove that proton. So we're going to get to another tetrahedral intermediate in this solution. Okay, and now what we need to do is we need to add a proton to that methanol group. And so you might be wondering, what makes this go in this order? It doesn't. You can be removing these protons and going back and forth, but if you have an excess of your alcohol overall, you're going to push it in this direction. So we're focusing on the steps that lead us towards the product. So we need to protonate this OCH3 to make it a good leaving group. It can't leave as methoxide in an acidic solution because methoxide is too strong of a base. So if we're going to protonate it, we need an acid. So our actual acidic species is the protonated alcohol. And we know that again because strong acids dissociate completely. So we are going to use that protonated ethanol as our acid source here. And so we can protonate that methanol in order to make it into a good leaving group. And so yeah, these mechanisms are long, particularly in acidic solution. We end up doing a lot of proton transfer steps to get to what we are looking for. So we're going to have another tetrahedral intermediate, but now we'll have one that we can lose a leaving group from because we're going to have a good leaving group on this structure, and it's going to be a good leaving group because it can leave as a neutral molecule. So now this is set up to reform the carbonyl and kick off that leaving group. So we are forming also methanol in this solution. And if we draw the product of this step, we are really close to getting to that final product. We have essentially the ester we're looking for that just has an extra proton on there. And so we've got the ethyl ester formed, it's just protonated. So the very last step is we need a base to remove that proton in order to get to the neutral alcohol. And also notice if this ethanol is removing a proton, you're getting back to the protonated ethanol, which is essentially the acidic species you started with. And this is an acid catalyst. So it makes sense that we use our acid in the first step, but then we regenerate it in the final step. So this is that final step. We're regenerating our acid catalyst, and you are making the ester product. So a really long mechanism. It follows the same steps as every nucleophilic acyl substitution. What you just want to make sure of is that you're in acidic solution. So you can have positively charged species, you can have neutral species, but you're never going to form something that is a strong base. And so you can use that as a guiding principle to moving your protons around.